So the basic goal here is I'm going to take a dynamical system, an IFS, and we're going to transform it into an action on a circle in such a way that the action on the circle still captures some of the stuff about the IFS. And then we're going to study the circle action because that's a little bit nicer than looking at a fractal. So that's the basic plan. And these are the IFSs I'm going to be looking at. They're the same as have appeared before, but maybe a little bit more specific. And I'm considering a parameterized set laser, where my parameter space is the open unit disk, and I just look at the dilation CZ minus 1, CZ plus 1. So those two maps for parameters C. And so, of course, what does multiplication by the complex number C do? It shrinks and rotates. And so F and G are going to shrink and rotate the same as complex multiplication by C, except, of course, they're going to be centered not at 0. So we know there's this attracting limit set, which is the union of F lambda and G lambda. Lambda, its defining property, is that it is that union. And it's going to have rotational symmetry by pi around 0 just because of the way that we constructed it. So I'm always going to draw, as in the first talk, I'll draw the limit set, which is the whole thing, as the union of the blue, F lambda, and the orangey yellow as G lambda. Okay, just to emphasize, because again, as we heard before, typically the interaction between F lambda and G lambda tells you everything about the limit. All right, so we already saw this too, so I'll just go quickly through it, but here's the picture about how you draw the limit set, right? We have these unions of balls, which we know are Hausdorff converging to the limit set, and we see that, so we can draw the limit set that way, and it's good. Okay. Oh yeah, and also this could be kind of important depending on what we get to later. Not only is the limit set sort of the union of F lambda and G lambda, it's also actually the union of, all words of length 3 times lambda, etc. Right? So it has this self-similarity on all scales, and you can make it as the union on all scales. And this is extremely convenient and basically how you prove everything. Okay, so the parameter space was the open unit disk, and I'm going to be interested in the set M for kind of Mandelbrot. The analog of the Mandelbrot set for this sort of situation, which is all parameters where the limit set is connected. Well, so that's maybe the definition that you make, but then there's this lemma that it says that actually the limit set is connected if and only if it's path connected, if and only if F and G touch. They intersect at just one point, which is kind of amazing. I mean, when you first see it, if you haven't really thought about it before, it's kind of stunning that you could have this set where, oh, I know that F lambda and G lambda, it intersects at one point, and suddenly I get the whole fractal is path connected. That's crazy. But in fact, it's not that hard to prove, and it just follows from the self-similarity that happens everywhere, and you can just build the paths explicitly. That's nothing hard. Okay, so if the parameter is not in the M, then the limit set is Cantor set, totally disconnected. And so we'll call the region where the limit set is a Cantor set Schottky space. Sort of, this is an analogy to the Schottky groups of hyperbolic isometries. All right, so here's a picture of parameter space. Well, of course, parameter space doesn't include these corners here, but it's this open unit disk. And the parameters that are colored white, this is Schottky space, so anything in here produces a Cantor set limit set. That's actually not surprising because if the dilation factor is quite strong, then you imagine that F lambda and G lambda are isolated from each other, and then you'll get this sort of Cantor dust immediately. But as you transition from, in here to out here, you have this very interesting boundary. And so actually, I should definitely mention this now. So these little whiskers on the real line, they're really there. And in fact, they are really just on the real line. There's a portion of those whiskers which is exactly the real line, doesn't have any interior at all. And what's interesting is that whether or not the neighborhood of that point is just the line, you can figure that out by looking at the attractor for an affine IFS, which is exactly the ones that were discussed in the first talk, and ask asking whether that one is connected, and that will tell you about the neighborhood of a point in this IFS. It's basically the affine IFS you get by looking at this IFS plus information that is derivative. Anyway, okay, so this set, if you zoom in on it, it becomes interesting on the boundary. There's lots of funky shapes, pretty much holes and spirals in any possible combination you can imagine of those. And yeah, so that's cool, and we'd like to understand what's going on here. So the holes, what's the deal with the holes? Well, the holes are everything we sort of defined here. I mean, it's defined in terms of these maps, which are just these contractions, but it's actually pretty hard to say things that are geometric about the limit set. But somehow the holes are a geometric property of the limit set. And what's going on? Right, here's the parameter. There's a little dot in there. I've drawn the limit set corresponding to that parameter. So it's in Schottky space. So this picture, although it does not look like it, is a Cantor set. But what you can see is that it's kind of geometrically linked in a way which is extremely difficult to formalize. But anyway, it is. You can see it. There it is. And if you try to drag this parameter from this hole out to the main region of Schottky space, you won't be able to do it. It's going to run into each other. The F lambda and G lambda will run into each other, and you will get a connected set. Apparently, right? I mean, who knows? These are computer pictures. Right? So, question one is, how could you even prove that this hole is really there? I mean, maybe there's a secret channel of right, they're Cantor sets. You could drag them through each other. Who knows, right? Okay. But no, we can't have fun with the Schottky program that draws these pictures. So there's kind of a long history of people studying these things. In particular, Bant proved the existence of a hole that one of these holes really is a hole. And so then maybe a little closer to home for me here, there's some more background. So Sarah and Danny and I basically came up with this. We did one thing, which was coming up with this sort of simple condition for checking whether the fractal, the attractor, was actually connected. And moreover, in the interior of this connectedness locus. So it's sort of simple to check, and so we have this condition, and then we just kind of did everything we could possibly do with this condition. In particular, we can prove the second theorem, which is pretty interesting, which says that the interior of the connectedness locus is dense in itself, away from the real axis. So this basically says that there aren't holes everywhere, right? There's really these nice regions of interior punctuated by some holes, and so that's kind of interesting. All right, so this is kind of the background, but there's some stuff which is still very mysterious. Even though we proved these theorems, and even though we can do things like certify infinitely many holes and all these other things, I mean, we can, with a computer, you can just draw a path that you'd like to certify, and it'll go ahead and certify that and say, yep, that's a path in the interior of the connectedness locus. There is a point in the middle, which is in Schottky space. Yep, you found yourself a hole. Okay, well, that's fine. But we really don't understand, we didn't gain really much understanding, actually, about why they happen. And they happen because of geometry, and so we'd really like to be able to understand something about the boundary of the connectedness locus. We know all about the interior. Well, we don't know all about it, but we know about the interior, and we can certify points as being in the interior, but we cannot do something like certify a point as being on the boundary of the connectedness locus. Can't do anything like that. So we'd like to try to gain some understanding of the boundary of the connectedness locus. All right, and that's what I'm going to try to talk about today. All right. Yeah. So this circle action that I talked about is going to come from a limit set corresponding to a parameter which is on the boundary of the connectedness locus. So we're going to take a parameter on the boundary, we're going to look at its limit set, and we're going to transform the IFS on the limit set to an action on a circle. And just as kind of an example theorem for something that you can do with this circle action, you can very easily check to see whether there are cut points in the limit set. Okay, so we're looking for a circle. There's an obvious, there's kind of only maybe one way to get a circle. And that's to use the exterior of the limit set. So the exterior of the limit set, if the limit set is connected, you don't need to be on the boundary for this. Right, it just needs to be connected. There's one connected component of the exterior, or the complement of the limit set. There's one which is different, and it's the infinite one. And you can uniformize the infinite one to the exterior of the unit disk. And the limit set is locally connected, which follows from the self-similarity again. And because of that, the map U extends to a continuous map from this circle to the exterior boundary of the limit set. All right, so there's our circle. And so now we're just going to follow that rabbit hole, basically. So what we're basically going to develop now is thinking about the circle as a proxy for the limit set. And we're just going to try to transform all of our questions about the limit set into the circle, and that's going to make our life easier to think about. So there's this proposition that you sort of need to get going, which is that if you're on the boundary, and you do need to be on the boundary for this, then you can divide the circle up into two halves, where there's a half corresponding to f, meaning that under this uniformization map, it maps to the boundary of f lambda, and then there's another half which maps to the boundary of g lambda. So an example of a thing which isn't happening is that, it's a little easier to see if I just point, there's not a region in g lambda that's sticking out over here, right? Because if there were, then as I went around the boundary of the limit set, I'd be in f lambda, and then I'd be in g lambda, and I couldn't actually do this. I couldn't make a whole half circle which maps onto the boundary of f lambda. Okay, but if you're on the boundary, in fact, you can do this. And then there's a conjecture which looks exactly the same, and I'll explain on the next slide why it's not exactly the same, which is that there's sort of a unique way of doing this. Basically, that the image of this half circle is exactly the boundary of f lambda, and this image of the half circle is exactly the boundary of g lambda. So I'm just, before you can even read the rest of the slide, I'm going to go to an example of why this is a thing. So this can happen. So f lambda and g lambda can intersect and overlap in exactly a copy of the limit set, for example. And so this is not on the boundary, apparently. I don't think we've actually certified that it's not on the boundary, but it sure isn't. And you can see that this sort of violates the conjecture. If I try to divide this circle up into two halves, yes, I can do it. The proposition says, the proposition I guess doesn't apply. But anyway, I can divide this circle up into two halves so that half maps to f lambda, half maps to g lambda. But it's ambiguous. There's many, many ways that I can do that. And this is unsatisfying. And so we want this conjecture. Essentially, the conjecture says that if you're on the boundary of the connectedness locus, so f and g, they must intersect because the limit set is connected, but basically they just touch, right? They just touch. There's no interval on which they overlap, okay? This seems like it should be obvious. It is obvious, we think. It seems like it should not be difficult to prove. We have no idea how to prove this. I think that this is a great, easily accessible question to think about, right? I mean, surely there must be some way to approach this question. This would be great to prove, and somehow this is maybe this is the deepest question, and we just haven't managed to prove it. Anyway, we're always going to assume that this is true. It basically turns all of our theorems from ifs, withs, to if and only ifs, or maybe if we didn't want to assume this, we could assume some other conditions or something like that, but we're just always going to assume this. All right. Okay, so now we're looking for an action. We have a circle. We've divided it in two. Now we want an action. And, well, where are we going to get the action? We already have an action on the IFS, which is f and g. So we're going to move that over to the circle in exactly the way that you would expect. So if I have the map f, which remember takes the whole limit set and maps it onto the f lambda, which is the blue part, right? So there is some interval, which I have drawn in blue, wiggly around here, which maps to the boundary of the blue part, which is also exposed on the exterior boundary. You can see that there's a little region in here which is on the boundary of the blue part, but which is not on the boundary of the limit set as a whole. And so I sort of don't care about that interval. I don't care about its pre-image under F over here. All right? But there is some interval on this boundary which maps to the boundary of the blue. And I can essentially just pull that back And then I have this interval on the circle, which maps to that interval. And then I can call that IF. And then there is a monotone homeomorphism from IF to JF. In other words, that just shrinks this interval on the circle down to the left half. And that commutes with the uniformization map. Rotation by pi, everything is swapping F and G is done by rotation by pi. So it's a monotone homeomorphism. This isn't like some deep thing, but anyway, this is just how we start to get the action. So we have this circle action. Now let's start doing some dynamics on the circle with it. So this is a cool thing you can do. You can make a lamination out of this action. So a leaf on a circle is just 2 points. But the way that we always draw a lamination is by connecting the 2 points in a leaf. Sorry, the way we always draw a leaf is by connecting its 2 points with a line. And we always draw geodesics in the Poincare metric of hyperbolic open disk because that looks nice. Anyway, so that's a leaf. And I'll say in a minute what a lamination is. But anyway, there's an obvious leaf here, which is we have these two sort of special points, which is where F and G meet. And so we'll make a leaf. We'll make that leaf, okay? And now we'll just start acting on that leaf. We have two maps. We have F, well, I guess I named them F tilde and G tilde for sort of the list of the circle, but we've got these two maps that we can just start acting on this leaf. So we've, right, there is a situation in which this is not defined, right? If the endpoints of these sort of intervals, F, like F is, I guess it's defined from this big blue interval to the left half. If one of the endpoints of the lamination of the leaf L were to end in this region where F isn't defined, then I just don't know what to do. And so I just say, oh, I can't do anything. But if both endpoints are in the blue interval, equivalently they're in the big orange interval, then I can act on it, and so I do that. And so I just keep doing it. And so I get infinitely many leaves, probably. Well, it's either finite, it's either the leaf L just by itself, or it's infinite. So yeah, and the lemma is that this is actually a lamination, meaning that these leaves don't cross. So this is sort of a lamination that's built out of the dynamics. And I mean, it's not, we're not doing anything magical here. You can sort of translate this over to what this means in terms of the IFS. We're just basically kind of taking this dividing line, and then we're mapping it around via F and G. And you can see that there's sort of some combinatorial information about how these things cut off the rest of the the limit set, and that's kind of captured by the way in which the leaves cut each other off. So it's just a nicer way of looking at it. So here's one of these guys to depth 6, I guess. They're cool, they're great laminations. Okay, so we actually built 2 circle maps. We did some dynamics. We haven't seen any theorems yet. But first, before some theorems, we're going to see how to package these 2 actions into 1 action. So it's a little unsatisfying to have 2, well, I don't know, depends if you like IFSs. But we'd like to have 1 map. It's kind of nice to think about iterating 1 map rather than 2 maps. And because of the way in which F and G work, we can produce 1 map. Note that F maps some interval down to the left half, and G maps some interval down to the right half. So we can just go ahead and define a map which does F inverse on the left, G inverse on the right, and just isn't defined on the right. Okay. So that's 1 circle action that I can do, and it just basically, now it's kind of even nicer because it expands. And so we've packaged everything up into this single map H, corresponding to some parameters. Okay. And based on the way that the lamination, the dynamical lamination is defined, it's immediate to see that the lamination is actually fixed by H. There's some funniness with the middle leaf L because it's kind of, I don't know what to do with it. Its image isn't defined, but it's in the image because leaves map onto it, in fact twice. So anyway, this lamination is invariant. Yeah, okay, so now let's sort of see some things that we can do with this circle action that might be interesting. So there's a theorem. This is kind of the technical theorem that underlies the next theorem, which is kind of nicer to think about and is the one that you might like actually use. So if I take any leaf in S1, not necessarily in the lamination, in fact it will not be in the lamination, it'll be in the closure probably. But anyway, if I take any leaf in S1, then the following two things are equivalent. The images of these endpoints actually have the same endpoint in the limit set. And furthermore, well, because of the way in which the uniformization map is constructed, that means that this point will be a cut point in the limit set. Okay, so that's one condition. And the other condition is that this h of the leaf is defined for all n. In other words, I can keep iterating h, which is equivalent to saying that this leaf always ends up with both endpoints on one half or the other half and doesn't cross. It doesn't cross from blue to orange. Okay, so these are two equivalent conditions. So this, if you kind of think a little bit about what is going on here, this seems like it sort of should be obvious. I mean, if you take a point and then you're able to kind of apply f or g inverse to it infinitely many times, well, if it's not a cut point, then you kind of you're expanding things every time. A point is the only thing you can expand infinitely many times, and it stays a point, stay bounded. Okay, so if you sort of think about this, it seems obvious, but it actually is. There's something going on, and there's some subtleness here that really needs the conjecture. You need this sort of unique choice of the left and right halves of the circle for this to really work. Okay, so we can make this theorem a little bit sort of nicer and turn it into kind of a finite combinatorial statement, which is pretty cool, I think. So first we need this word that interact. I don't know, this is not a general definition, I just made this up. So two leaves interact if they cross or if one hides the other. Oh, I guess I defined hide too. Anyway, I think you know what it means. But they don't do this. So these two leaves are not interacting. They're just sitting on their own doing whatever. But these two situations on the left are interacting. All right, so here's sort of a classification theorem. So what I do is I take this middle central leaf L, and then I act on it by F inverse. So this will not be in the dynamic elimination. That's not something that I do, because I don't know how to apply H to this map, because it's ambiguous whether I apply F inverse or G inverse. But I can just go ahead and apply F inverse. Okay, fine. So I do, and I get this leaf over here, LF. So that's some leaf in the circle. Okay. Now I start generating the dynamic elimination out of this central leaf, and there will be some leaf in the dynamic elimination of least depth which interacts with this leaf LF. It must. There must be some leaf in the dynamic elimination that interacts with it. In other words, hides it or crosses it. This situation on the right actually can't happen. So if this happens, then yes, the limit set has cut points. If this happens, there are no cut points. Okay? So notice that this is like a finite thing that I just did, right? I have some maps on the circle, and I started applying, to build the dynamic elimination, I apply F and G to the central leaf and take the orbit, but at some finite depth, it's going to interact. And at that point, I'm just done. And then I will get, I will know whether or not there are cut points in the limit set. So an example of this happening is this limit set over here. I already sort of drew a picture suggesting that, in fact, yes, there are cut points. Well, you can kind of see where they might be. But we can apply the theorem to see that this is true in a finite amount of time. We can just go ahead and start generating the dynamic elimination. We see LF here is hidden, and if you'll recall, that said, yes, cut points. So, yep, there are cut points, and we sort of know that from this finite amount of information. Here's another situation where the opposite happens. I have this leaf over here, it's crossing it, so I know, nope, there's no cut points. We see that in action. So maybe I'm gonna have to skim through this because for lack of time, but you can sort of even go farther, and you can build these graphs where the cut points in the limit set correspond exactly to infinite walks in the graph, and so you kind of like capture the cut point structure of the limit set with a finite combinatorial object. It doesn't theoretically have to be finite, but you can generate it, and you can know when you are done, and it always has proved to be finite. So, okay. And you can get some pretty cool structures for sort of the limit set structure, or cut point structure. Okay, but this one I think is maybe the most theoretically interesting because, so I've kind of been brushing under the rug how you might like actually computationally do this. And in particular, I've also been brushing under the rug how you might like apply the map on the circle. Because so there's this uniformization map, and we know what f and g do on the limit set. And there was this proposition that said that you can sort of pull these maps back to maps in the circle. And they're monotone homeomorphisms. They're nice things. Sorry, they're monotone. No, yeah, they are monotone homeomorphisms. They are nice. However, it's very difficult to know like what they are, right? And so this theorem says that in fact, you can actually conjugate, there's a conjugation of the circle which actually transforms the maps f and g to linear maps. In particular, there's this one map H. So suppose I want to do a linear version of what I just described. Well, there's two parameters associated with that, right? I take this left half, and I should dilate it by some amount, and then I should rotate it by some amount, okay? And then I get g by doing exactly the same thing, just flipped by pi, right? So that's kind of a linear model for this kind of action. And the theorem is that for essentially all parameters, the circle action is actually conjugate to a linear action. And so one thing that's pretty interesting about this is that you get these two parameters, the rotation and scale parameters, from the circle action that are built out of the IFS. Now, the IFS is built as the attractor for these dilations, right, in the complex plane. And there's a scale parameter and a rotate parameter, right? They're there. They're not the same at all. So that's what's kind of interesting, right? Now, I mean, it's of course that is possible, right? You're essentially taking this fractal thing whose boundary, whatever, whose length, I mean, that doesn't even really have a length, but it's kind of infinite, right? And so there's this infinite thing getting scaled onto itself, and then you're coming up with a new scale parameter, and it doesn't really have anything to do with the original scale parameter, which I think is really interesting. So you kind of get this invariant out of the IFS, and it's not clear really what it means, actually. But there should be sort of something to do with this, and this should be sort of some thing that captures some geometrical information about the IFS.
Sorry, like 1 or 2 minutes.
Oh, 1 or 2. Oh. Well, anyway, I'm pretty much done. Here's a cool picture. That's it.
Questions?
So I mean, clearly this is like modeled on Dewey Hubbard for Jolla sets, right?
Yeah.
And the big difference is that you have this gap.
Yeah.
But when you talk about you have a scale parameter, you said that the scale parameter could be between 1 and 2, and equals to 2 was in there, right? So if it's previous slide maybe.
Yeah.
Scale parameters, scale by
Yes.
1 less than equal to lambda less than equal to 2. So if it's equal to 2, do you then just end up with literally Dewey Hubbard?
Okay, right. So 2 would be the top, and what does that correspond to? 2. Oh, right.
Yeah.
Yes.
By 2, you actually you have no
you
gap,
get the whole circle.
right?
Yeah.
So then is it just Dewey Hubbard, or is there something else that can happen? Because I mean, like, obviously the dynamics of something much more on the circle is something much more complicated once you've got a gap.
Yes. Oh,
But
yeah.
if by chance you just luck
don't.
out and there's no gap,
Yeah, I know.
then
It's
just
sort of-
all purely.
So the actual answer to your question is I don't know, but
Okay.
probably. But so here's a picture. Okay.
Lambda equals 2.
I got loop. Oh, okay. Yeah. So stuff happens when lambda's 2, and you can do some stuff, and you get a picture that looks like this, which looks like a picture that you generate from a lot of other things. And so the answer to your question is probably yes, there's some connection. But I don't, yeah, so I can't formulate a intelligent answer to your question, but the answer is probably yes.
Sort of books.
Yeah.
Okay.